So, good afternoon, everybody, and good morning to some of us, especially our main speaker today, who is Professor Eric Popp from Stanford University, who is in a different time zone and is now at 7 in the morning, I think. So we're very grateful to have him here. We'll start the event, this nano seminar on physics. We'll start it with a talk given by Emigdio Chávez, who is a postdoc in a group of Clivia Sotomayor. So please, Emigdio, start your presentation.
Okay, thanks for this introduction. I will just check now. Okay, I will introduce a little bit part of the work of our group, which is now entitled Anisotropic Thermal Conductivity of thin diselenide or layer 2D thin diselenide. This work was developed due to two European projects. One is focused on the electronic properties of 2D materials, which is the nanopoly, and the other is focused on the acoustic and how you can manipulate the acoustic properties of using 2D materials. This is the ERC of Clivia, the late project. Okay, a little bit the introduction. I will start to speak about some properties of the thin diselenide, why we're interested in this material. I will also introduce a little bit the fabrication for measuring the in-plane and cross-plane thermal properties. And the last part is just introduction of the anisotropic thermal conductivity together, but very briefly, the Phononic mean free path distribution, which we obtained from the experimental data. Well, why thin diselenide? As you can see over here, between the 2D materials, the thin diselenide is one with the lowest thermal conductivity, which is around 3.8. This is for bulk values. This quite low thermal conductivity, together with the relative high Seebeck coefficient, make it a quite interesting material for use as a thermoelectric system. Indeed, a family of thin selenide, have nowadays one of the largest thermoelectric figure of merit. This is the case of polycrystalline thin selenide, the bulk one. But you see here the ZT is quite outstanding. This is around 3, and this is very high in comparison with the rest of materials. This is why we are interested in particular in this material. Well, the fabrication. This is an example of a typical sample. This is a freestanding 30 nanometer thick thin diselenide, and the way to fabricate it is basically summary in this picture. We start with silicon nitride TM grill. On top of this silicon nitride TM grill, we deposit metal, we deposit titanium and gold. This is to ensure a good thermal sink. And after that, we are doing dry transfer on top of the hull. The hull is important in order to measure or to ensure the thermal transfer is along the plane of the system. In this way, we also are able to couple a second laser and measure the thermal properties. I will show in few slides. And this is the typical examples. This 25, 40 nanometers. There are many samples deposited in the same way. First gold, well, titanium gold, and later just a Scotch tape on top the different samples. Well, to measure the in-plane properties, we are using one technique developed in our labs, which we call it two-laser Raman thermometry. The technique consists in to generate a hot spot in the middle of the membrane, and with a second laser, we measure the Raman peak position as a function of distance. Then at the end, as we know, the Raman depends on temperature, is shifting to lower energy. That is because there is change in the atomic forces. And at the end, this is a good way to prove the local temperature. Once we are doing the peak position as a function of the temperature, this means we are calibrating our thermometer, we are able to do some thermal mapping through the system. This is an example of silicon. It's a very old sample, but I always use it for example. In this case, the hot spot is generated by this blue laser, which is fixed at below the membrane. And on top, we are measuring just the Raman. But as we know, the peak position dependence with temperature of the Raman signal, we translate that to temperature rise. And later, when a model, either COMSOL, or also there is an analytical way to extract the thermal conductivity, we can extract the in-plane thermal properties. And with that, we ensure we are always in plane, because the heat sink that you saw in this slide is in the surrounding of the system. We also create this whole circular in order to facilitate the simulations. Okay, this is for the in-plane properties. For the cross-plane properties, we study a different approach. In this case, we want to study the same sample, the same system. Then once we finish all the measurement of the thermal conductivity in plane, we deposit 100 nanometer gold on top of the sample here. And later we deposit around 1 micron nanometers at the bottom. And in this case, the idea was to use the frequency domain thermoreflectance to measure just the cross-plane thermal properties. However, as you can see over here, the system is a little bit more complex than before, because before we just have a hot spot which generate well, the laser below generate a hot spot, and all the heat will propagate through the plane. But now we have more things in the system. We have a transducing layer for the frequency domain, which have its own unknowns, like the thermal conductivity and the heat capacity. Later, we have the interface thermal resistance. Later, we have all the unknown of the field, the cross-plane, the in-plane thermal conductivity, specific heat capacity. Again, another interface thermal resistance. And at the end, we also have the bulk, the substrate, with its own thermal conductivity and also heat capacity. In order to reduce the amount of unknown, we first measure the electrical properties of the transducer in a separate sample, and also the electrical properties of the substrate. Then, as we know, the gold is a metal, then the main heat carrier are electrons. We can use easily the Biden-Franck's law, and we estimate directly the thermal conductivity by using just the 4-point technique. We did that for the transducer and for the substrate. It's very close to the bulk value, but it's not bulk. I don't remember by heart, but it's not bulk. And the heat capacity, we take it from the literature. We didn't measure, but it's also possible to measure with another technique. Finally, once we have all this unknown, we estimate the thermal properties of the film together with the interface thermal resistance. Then, to understand properly our system, we run some simulation about the sensitivity of this frequency domain. We can see in this example over here, we start with very low thermal conductivity, just to give a number. We put at the first number a very low one, and quite high anisotropic ratio, and the same number of thermal conductivity and a small anisotropic ratio. And we see we are only sensitive to the QZ, which is the cross-plane thermal conductivity. The anisotropy, either for large or small value, we don't see it, or we are not sensitive at all. We are not so sensitive to the specific heat capacity. That means at the end, we think the sensitivity just depends on the cross-plane thermal properties. We did also for other systems with larger thermal conductivity, and at the end we did a map of all the possibilities. That means we take thermal conductivities varying from 0.1 to 2 to 3, and we just do a loop. And at the end, we always be sensitive to the cross-plane thermal properties. These are the results. Here we see the in-plane thermal conductivity together with the cross-plane thermal conductivity as a function of the thickness. The interesting thing we will also see is possible to use the well-known Fuchs-Heimer model to fit the data. And with that, you can extract an effective mean-free path, but also you can extract a mean-free path which depends on accumulated mean-free path, which is called a reconstruction mechanism. I will speak just briefly about that because I don't have so much time. And finally, just by dividing the in-plane by the cross-plane, we can extract the ratio of the thermal anisotropy. Interesting, we found it oscillate between the error bars at the end, but it's more or less constant as a function of thickness. Similar result was also found in other materials. That's been thickness independence of this thermal anisotropy, as is the case of black phosphorus, as also is the case of the indium diselenide. And well, this is more or less the summary of our measurement. And just briefly, by using this experimental data, the black dot and the red dot, together with the Fuchs-Heimer, we also extract the mean free path distribution function. Also is reported in this article. And we can observe the mean free path distribution function obtained for this experimental data match quite well with the theoretical values predicted by other authors. And at the end is an extra information you can extract from this thickness dependence measurement of the thermal conductivity, either in plane or cross plane direction. Well, this is some short conclusion. We found the typical dependence of the in-plane and cross-plane thermal conductivity. We used the Fuchs-Onheimer to extract at the end the Phononic mean free path distribution. It was very interesting to see the anisotropy ratio is around 8 and it's almost independent of thicknesses. And the thickness independence of the thermal conductivity, the anisotropy ratio, we don't know why this is constant. And we think we need more investigation about. But this is all the team was collaborating in this article. Clivia, which is the group leader, Alexandro, Mariana, and Peng Chao. Thanks a lot for listening.
Okay, Emigdio, thank you very much for your presentation. I think it was a very interesting topic. So now the floor is open for questions. There was nothing in terms of questions related to the talk in the chat, I think, unless I missed it. Is there anyone who would like to ask a question? Please raise your hand or write it in the chat. Or there is something. Yes, there is a question from Nakib. Thanks for the talk. Do you have measurements on a monolayer?
Yeah, on monolayer, we don't have, because we are doing exfoliation, and to obtain a large area of monolayer thin dyselenide is complicated. We also have on top of a substrate, but we are doing the analysis still of this kind of membrane, of this kind of samples. But suspended, no, at the moment.
Okay. Any more questions from the audience? Yeah, I think. Yeah, there's another questions from Chiyu Yang. Thanks for the presentation. I am wondering why the laser heating is chosen compared with other heating methods.
Because it's simple. This is very easy. We just have to put the sample in a hole, and it's very straightforward to generate a hot spot and later measure when Raman. It's just because this is the simplicity of the technique. But of course, there are more things like measure the absorbed power, well, measure the spot size and things like that. But if we compare with others, characterization technique is very simple. We don't need to add anything else. Just the sample, either in a freestanding hole, can be also used a substrate with low thermal conductivity, or what is also possible to measure in a substrate just with hole, but not through the system. I mean, if you pattern small holes, using one laser is also possible to measure the properties.
I see there are two more questions. So one question is, actually it's one question. So do you have a theoretical understanding of the thickness dependent thermal properties, phonon modes, etc.?
We tried to run very fast in this article, then we didn't ask for any help in the theoretical aspect. We just extract at the end the mean free path distribution. But we think with these thicknesses, at the end, the phonon mode will not affect so much the thermal properties. It's quite thick, the system. It's not one layer or two layers. You can see over here. Yeah, here's up here. The thickness is above 10 nanometers. Then if there is any effect of a modification of phone dispersion relation, which should not be affected. I mean, quickly you achieve the bulk dispersion relation. And at the end, we are thinking that still the diffusion model is still hold. I mean, the Fuchs-Onheimer model is still hold. And at the end, it can be treated as a thin film.
Okay. I think we are running out of questions, and I think we're perfectly on time to move to the main event. So let's thank Emigdio Chávez again. Thank you for your talk and for staying very nicely on time. So we'll move to the main speaker, who I should mention we should all apologize to for actually the fact that we made him get up very early in the morning, because he is based in California. It's around 7 in the morning for him. So while he is getting set up, I will introduce the biography of our speaker. So Eric Popp is a professor of electrical engineering and material science and engineering at Stanford University. He was previously on the faculty of University of Illinois. He also worked at Intel for a few years. His research interests are at the intersection of electronics, nanomaterials, and energy. He received a PhD in electrical engineering from Stanford and 3 degrees from MIT. He has many honors, including a Presidential Early Career Award, a Young Investigator Awards from the Navy, the Air Force, the NSF, DARPA, and several Best Paper and Poster Awards with his students. In 2018, he was mentioned as one of the world's highly cited researchers on the Web of Science. He is an editor of 2D Materials, served as a general chair of the Device Research Conference, and he is on many program committees and conferences. And there's also some fun facts in his biography. So in his spare time, he tries to avoid injuries while snowboarding. And in a past life, he was a DJ at what I think is a Stanford-based radio station. So we're very happy to have you here, and we're very much looking forward to your presentation. Thank you very much for joining.
Thank you. KZSU 90.1 FM, Stanford University Radio. That's how I introduced myself 15 years ago. Thank you so much for the very generous introduction and for the invitation. It's a pleasure to be here. Maybe I should start by sharing the screen. So I titled this talk, What Are 2D Materials Good For? Because it's one of the things that we're searching for in my group. And I think it's a nice combination of both our electrical and thermal efforts over the last few years. Again, I'm with electrical engineering and material science engineering at Stanford. We have these 2 websites, poplab.stanford.edu and 2d.stanford.edu, where we put some material sort of transistor benchmarking data that we've been taking from the literature. Just to show you where I am right now. So I'm here at Stanford University right now. And so we're about 50 kilometers south of San Francisco. Recently, if you probably heard about the fires, the whole country's been on fire, at least California's been on fire, I should say. Lake Tahoe had AQIs on the order of 700. Basically, they had to evacuate South Lake Tahoe. This is actually normally where we go snowboarding or skiing with the students, because the mountains around the lake are pretty tall. This was a year ago, showing the air quality in most of the US. And you've probably seen these very terrifying images from San Francisco a year ago. But when it's not the apocalypse, this is what our campus looks like here at the bottom. So this is the main quad and the main church, and sometimes we even teach in these buildings near there. All right, so having given you the weather report, I should talk about nanotechnologies, and I've organized the talk sort of in a way that I'll start pretty broad, then I'll go pretty deep, and then I'll zoom out again. But while preparing an earlier version of this talk, I went and I looked at a number of nanotechnologies that I happen to be familiar with. So this list is very personal, obviously. I've worked on phase change materials. We do a little bit of work with oxides, LEDs, carbon nanotubes over the years. And so on the left, you can see the date when the nanotechnology, or technology, if you will, was proposed. Let's say GMR was in the mid 1980s or late 1980s, and then when it was commercialized on the right, and the company that I think seems to have commercialized it. And among these technologies, the IGZO TFTs actually seem to have the shortest time to commercialization, And then here we are at the bottom, carbon nanotubes, graphene, and 2D. Carbon nanotubes, of course, have been around since the early 90s, graphene since 2004. And there's question marks here because we're not sure what they're good for. I want to specifically highlight IGZO because IGZO was published in Nature 1 month after the Novoselov and Geim graphene paper. And it was commercialized by LG and Apple in our displays in about 10 years. So it's very, very quick from discovery to commercialization. So it is clearly possible to take a completely new material and to put it in consumer products and to just have it usable within 10 years. This is amazing to me. Now, the interesting question is, why did IGZO succeed so quickly? And the answers that I found, partly reading this nice short paper by Hideo Hosono on Nature Electronics, is there was a clear need for something like this. For example, the mobility and the transparency were better than the existing solution, which was amorphous silicon in displays at the time. And then it turns out the production process and the integration into displays were actually very similar to amorphous silicon. It can be deposited over very, very large areas, and people didn't really have to invest greatly into new equipment and so on, right? And people could also get sputtering targets and so on. So again, to me, this is a remarkable success story. Then the flip side of the coin is, why do some nanotechnologies not succeed, right? And so here's I talked to, this is not just my slide, but I talked to a number of experts, both in academia and industry, to make this slide. And I came up with a few bullets. One is, it's not better than existing technology, right? But not only that, keeping in mind that the existing technology may have a huge existing infrastructure, which can be repurposed, for example, silicon or amorphous silicon, and so on. The second bullet is, you can make 1 or 2 of these things in the lab, write a Nature paper, but it doesn't work in the real world because it's not reliable or not scalable at the 1 million to 1 billion scale, maybe because of defects and so on. And maybe sometimes there's not enough effort to make it scalable. People sometimes dismiss this as just engineering, but just engineering is actually very, very difficult to make something workable. In some other cases, and we academics are guilty of this. We overhype some results and then we underdeliver, right? For example, carbon nanotubes, in my opinion, are a classic example. When I was a graduate student more than 15 years ago, there were news stories coming out everywhere saying that Intel will soon have a carbon nanotube driven, processor. And of course, you know how that turned out. Intel is still happily making silicon-based processors. Well, I don't know how happily, but they're still making them based on silicon because silicon is good enough, it turns out. And carbon nanotubes are just way too complicated to make high-performance electronics with, at least at that scale. Having said that, blue sky research does remain very important, as does continued funding. For instance, if you look at gallium nitride, gallium nitride was first essentially discovered or used for blue LEDs in the late 1960s, and then people just kind of forgot about it and lost patience. And then it was in the wilderness for about almost two decades until Japanese researchers resurrected it in the 1980s and really made it work by the 1990s. But if we had continued working on gallium nitride when it was first proposed in the 1960s, we would have LEDs and white lighting and all the other stuff probably 10, 20 years earlier. So it's amazing to me that gallium nitride actually took as long as it did. So I don't have a real answer, but I hope this is thought-provoking. The other thing that I did is I looked at the number of publications on the subjects that I showed you earlier. And I want to warn you, this is a very unscientific comparison. This is from the Web of Science, just search by topics. And you see IGZO has the fewest publications, right, by far, because it went from Nature paper to Apple displays, iPad displays in 10 years, right? So there's just not that many papers published on it. On the other hand, you see carbon nanotubes. I found over 70,000 papers, and surprisingly, I found graphene even many more papers than nanotubes now, over 200 and maybe 250 to 300,000 papers. So maybe one answer to my question, what are 2D materials good for, is they're good for publishing. They're good for publishers. They're good for publishing. They're good for science, for sure. And they're good for education. meaning they're good for educating, PhD students who then go on to Intel and Apple and LG and Samsung, at least from my lab, to work on, things that work in commercial settings. So that's one view. Of course, this is slide number 7, and the talk has more than 7 slides. So you can see that despite the sort of reality check kind of introduction, I hope you will conclude that I am an optimist at the end of this 45 minutes. So let's talk about 2D materials, at least with my very biased electrical engineers, at least engineers' view. So first, if you're new to the field, what are 2D materials, 2D or not 2D, as this character here on the right says? To me, 2D materials are monolayers, primarily monolayers. Monolayers are the most special and the most unusual. They're 1 to 3 atom thick materials. They can be metals, insulators, semiconductors. I think films greater than about 5 layers are essentially 3D. They're anisotropic, but they're 3D materials. So it's really just the monolayers and maybe the bilayers that are very special from an electronic or optical point of view, at least for the kinds of applications that I will describe a little bit later. The other reason I think they're so special is because they interact with their environment with van der Waals bonds. What that means is that we can do heterogeneous integration. We can integrate them onto other substrates without lattice matching, right? So that actually means that we can grow crystalline, 2D materials directly onto amorphous substrates, as we have done, and as I'll show in a moment. Or we can peel and stick these things for one substrate and put them on another substrate, and then we can obviously, create things at scale like that. Okay. Since we're going to talk about some electrical and thermal properties of 2D materials, I think it's worth putting up the band structure and the phonon dispersion, at least for MOS2, which is a very common 2D semiconductor, but it's pretty representative of others as well. So in bulk, it has an indirect band gap. And then when you grow it or reduce it to one layer, there is a direct band gap of about 2.3 electron volts. I want to point out that the direct band gap for MOS2 is larger. The electrical band gap is about 2.3. The optical gap is 1.8 or so. So the energy difference is because of the strong exciton binding energy, but the electrons experience a 2.3 EV band gap or so. Depends on the environment, like the dielectric environment. But then if you strain it, weird things happen. Mobility can increase, the band gap can decrease, all kinds of things can happen. And actually not that much is known about straining these materials, it turns out. Then here at the bottom, there are phonons. Phonons are the lattice vibrations, the atomic vibrations, which are responsible for the primarily the thermal properties of these materials. The main takeaway message here, which we'll come back to, is that the phonons are very anisotropic. So the in-plane phonon dispersion, the in-plane phonon velocities are much faster than the cross-plane thermal velocities, which leads to significant thermal anisotropy between the in-plane and the cross-plane directions for these materials. Okay, so the other question that I find very fascinating is how many 2D materials there are and how are they going to succeed in anything. I have a colleague, Professor Evan Reed at Stanford, who has recently told me that there's actually over 1,000 2D materials that exist out there. He's written papers about this. He's a computational material scientist. And in one of these papers, he ranked the 2D materials by band gap. So for instance, you can see there's over 150 of them that have, 0 band gap like graphene. There's about 160 that have, band gaps like MOS2, and about 26 that have band gaps like boron nitride, very large band gaps, right? And the joke that I made out of his findings is that there are more 2D materials than there are Avengers. And there's a lot of Avengers. I lost track of how many Avengers there are in the Avenger universe. Now, which ones of the 2D materials will succeed? Also, my opinion is there's those with unusual properties and those that don't have a bulk analog. Because wherever we have a bulk analog that is good enough, I think it's going to be very, very difficult, if not impossible, to displace the bulk material that is already good enough. Having said that, clearly, if we're just working on 1 or 2 2D materials where this field is very vast, probably very under-researched, under-synthesized, under-tested. So it actually needs a lot more discovery and testing and funding, to be honest, I think, because there's so much more to discover. All right, so what are some of the existing applications of 2D materials? It turns out, again, from a quick survey of, and if you want to call these 2D materials, a quick survey of things, the applications that I see today are basically bulk composites. You can buy these lubricants. In fact, I have these graphite dry lube for my bicycle chain, or something very much like it. And then if you're a fan of Novak Djokovic, he will sell you, or his representatives will sell you a graphene racket, supposedly for about $220. At some point, I read that Novak actually does not play with this racket, but this is, I think, the racket that he advertises, if you sometimes notice. But of course, these are composites. You might say these are probably, based on bulk graphite and moly disulfide. All right, so I think that's fine, obviously, but that being a nanotechnologist, I'm interested in applications which take advantage of the atomically thin nature. I really think that's where these things are unique, is when you're talking about applications which really take advantage of the fact that these are 1 to 2 atoms, 1 to 3 atoms in thickness in the monolayers. So one example from my personal work with Professor Rashid Bashir at University of Illinois is making these DNA sorting nanopores, because if you want to essentially sort through DNA and be able to detect individual base pairs as the DNA goes through a nanopore, you really need a material that is as thick as the spacing between the DNA base pairs. And that spacing is, about 0.3, 0.4 angstroms, something like that. Sorry, nanometers, 3 to 4 angstroms, meaning 0.3, 0.4 nanometers, right? And so, this is basically our only chance for doing something like that. So I like that example, even though we don't do that much work on it right now. A bad example, in my opinion, is doing anything with thick materials, especially thicker than about 5 nanometers. There's been a lot of work done with black phosphorus transistors, which in my opinion, especially if they're very thick, in my opinion, is not that interesting, because you can do this kind of stuff with silicon or germanium much better. Especially germanium has good hole mobility, probably better than black phosphorus, and there's so much infrastructure for both silicon and germanium, and they're much easier to work with. All right, so having said that, there's if you want to push this towards applications, you can't rely on the Scotch tape method. And of course, in this field in 2004, people began to Scotch tape exfoliate these things, right? But the joke in my lab right now is that we've banned Scotch tape, so there's no more Scotch tape in the lab for about 5 years or so, and we grow everything that we use. We try to grow everything that we use, either by chemical vapor deposition or by chemical vapor transport. And so here are some examples of the things that we grow: boron nitride, zirconium selenide, hafnium selenide, monolayer moly disulfide. We etch the obligatory, Stanford logo. This is about 2 centimeters by 2 centimeters, the Stanford logo there, maybe a little bit smaller than that. And then if you look at the, this is one of my students recently etched the face of Dr. Anthony Fauci, who is the lead of the anti-COVID response in the US, which I don't think Anthony Fauci knows about this, but he's too busy fighting COVID anyway. And then, so, in academia, of course, we can do things on centimeter scale if we can grow them, maybe up to 100 millimeters. But at IMEC and Intel, I think now, they're able to grow these 2D materials on 300 millimeter wafer scale, which is really impressive. And I'm really happy they're doing that, because obviously we can't do anything at that scale. And IMEC is already reporting, for example, transistor threshold voltages over 12-inch wafer scales, which I think is very, very important, and very nice to see this kind of work from people who can do it. Okay, so some of my biased views, and now we're going to drill a little bit deeper into my group's recent work. But before I do that, I want to make a distinction between what's known as Moore's law and Denard's law. Certainly, as an electrical engineer, I hear Gordon Moore's name almost every day. But I want to emphasize that people have often confused Moore's law with Denard's law. Moore's law was really about complexity and cost. It's a law of economics, essentially, that basically says, look, if you can cram more transistors per square centimeter, then you're going to be able to sell more complex systems as long as you can do it at a decent cost. Denard's law was about making those transistors smaller. right? And of course, Bob Denard's prediction of making transistors smaller is now sort of almost running out of steam because we're getting to atomic scale transistors, almost even in silicon. But a lot of people talk about the end of Moore's law when they mean, probably they mean the end of Denard's law. Moore's law is a law of economics. And in my opinion, Moore's law is far from ending. In fact, I'm going to argue that Moore's law is going 3D, which is why Gordon Moore in that picture is wearing 3D glasses. So how so? Why do I say that? Well, the problem with computing today is that the logic, the computing processors and the memory, data storage, are on separate chips, right? You have Intel who makes the CPUs, let's say for our computers, and then Samsung or Toshiba or Micron who makes the memory chips, and they're separate chips, and they're connected by a bunch of long, copper wires on the motherboard. And so this is extremely energy efficient. You have to run data back and forth between memory and logic. And as you know, it just uses up your battery and so on pretty quickly. Data centers use up a lot of energy and so on. And so the obvious solution, I think, to this is to stack these things in 3D. And this is perfectly consistent with Moore's law because ultimately you're improving density, but you can improve density without necessarily making transistors smaller, which is, I think, the spirit of Moore's law, the correct original spirit of Moore's law. My colleagues here at Stanford have essentially done some calculations, and they've shown that if you do this kind of 3D integrated, very, very closely integrated logic and memory, you can get up to 1,000 times benefits at the system level, because now you can get data back and forth much, much more energy efficiently, simply because things are closer together. And so the corollary for me is that Moore's law is not dead, it's not dying, it's not even sick. It's actually going 3D, and of course, Denard's law will be probably, eventually reaching atomic scale, but maybe it never will. If it doesn't have to, right? If we can just build things efficiently in 3D. So here's a slightly more sophisticated, maybe, image of that 3D heterogeneous integrated chip that I described earlier. I think there's a lot of room for 2D transistors and 2D thermal, heat spreaders, as well as 2D, memory, or 2D driven memory inside a chip like this, for reasons that I'll explain in a moment. But before I do that, maybe I should say, one of the questions that I often get working in this field is, are you going to replace silicon? And I always, say we're not going to replace silicon. Silicon will be here forever, as long as we live on planet Earth, because it's the second most abundant element, and it's good enough for a lot of stuff. But there's some things where, again, maybe being an optimist, I think 2D materials are better than silicon, and one is this kind of a 3D integration scenario. The thing is, silicon compatibility is required. And if you're going to stack things in 3D like this, this is called the back end of the line kind of integration in silicon language. This means that you have to be able to do this at temperatures below about 500 Celsius for about 2 hours. At least that's the current dogma. This is what we currently think about back end of the line silicon compatibility. And of course, some of the 2D materials cannot be grown below 500 Celsius, at least not yet. So layer transfers or low temperature growths become very important. I do want to emphasize that this 3D architecture is by far not something invented at Stanford. In fact, it's been around for a while. If you look at memory chips, memory companies have been doing 3D memory for at least 10 years commercially. This is a cross section of a 32-layer vertical flash memory. And I think this is the memory inside my laptop right now. And I think today, if you buy the newest laptops and cell phones, you have 96-layer flash memory, all vertically stacked. And I think Micron recently announced 2 times 88-layer. So they're probably going to get to 1,000 layers pretty soon, which is why the price of flash memory is amazingly low, and it keeps getting lower, just like a miracle. And then if you look even further back, you look at architecture, you see that 3D architecture has been around even longer, and for very similar reasons, meaning that you can do more energy efficient people storage, people and goods, right? If you stack them in 3D, because tall buildings are much more energy efficient per occupant or per square meter than there are small houses that are just scattered around, in suburbia, right? Okay. of course, as electrical engineers, or at least the electrical engineers in my group, because not everybody in my group is an electrical engineer, are very, you would say, obsessed with silicon. The problem with silicon, of course, is that 60 years of silicon has gotten us almost to single atom transistors. Not there yet, but very close. This is a gloriously beautiful image of a cross section through a 14 nanometer Intel FinFET. Notice that there's no 14 nanometer dimension here. This is 8 nanometers wide. It tapers off. It's a little bit wider at the bottom. The current, by the way, flows in and out of the page. And electrons travel through this, but they scatter against these interfaces. So this very nicely also highlights what the problem is. The problem is when you thin down and scale down these bulk semiconductors, the interfaces are very, very bad, right? The band gap variability comes into play, mobility variability comes into play, manufacturing, of course, variability, right? And so we've kind of backed ourselves into a corner where we can't really thin silicon down anymore in these FinFETs, right? Or an SOI or nanosheet transistors or whatever you think in silicon, right? And so if you want to make thinner materials, you really only have one option. And in my opinion, these are what I call these 21st century materials, which are either carbon nanotubes or the 2D semiconductors, right? And the reason for that hopefully becomes clear when you look at mobility as a function of thickness. If you look at silicon, the mobility becomes very small if you go below about 4 nanometers in thickness. But then if you look at these 2D materials and graphene and carbon nanotubes, the mobility is very high, or at least it's reasonably high compared to silicon for films that are thinner than about 4 nanometers, especially in 1 nanometer sort of monolayer films. And this is also why I was emphasizing earlier that materials thicker than about a few layers don't really make sense, at least for electronics, because silicon and germanium are already so good, as are things like indium antimonide. Indium antimonide has, at least in bulk, it has mobilities greater than many graphene studies, right? And this is a semiconductor with good electron mobility. And then if you want good hole mobility, germanium has mobility in the thousands as well in bulk. But people have also shown really good germanium mobility in thin films at room temperature. And so I really think these materials shine and they become very, very relevant at monolayer or maybe bilayer thicknesses for these kinds of applications. I should mention that some of the reports of mobility in the literature for these materials are incorrect. Some very famous reports are actually incorrect. Some people have written papers about how they're incorrect or how they should be fixed. Some results are out there still not corrected, but it's just important to kind of look at the average results and see what the consensus is. If the result looks too good to be true, even if it's published in Nature, it may not be true. And personally, I think that because mobility is so difficult to measure sometimes, current is just a better metric. You can measure current, you know exactly what you're measuring in milliamps, and people should just report current per width of a transistor as opposed to the mobility, or report mobility and current at the same time. Speaking of current and speaking of nanoscale things, of course, when you have access to a reasonable academic sort of manufacturing facility, we've tried to make sub-100 nanometer transistors. And, even 5 years ago, we made these 10 nanometer gate transistors in my group. Here's the IV curves. You can see the current goes up, it saturates. It looks almost like a textbook transistor. Not a very good one, but it kind of looks like one. And at the time, the current was the record 400 micrograms per micron. This is a saturation current up here. But it was very clear that these transistors were limited by their contacts. The contact resistance down here was pretty bad. The transistors were also difficult to shut off. And the current here had negative differential conductance because it turns out these things heat up quite a bit when they operate because you're pushing a lot of current through a monolayer material. More recently, these are sub-100 nanometer scale transistors on a flexible plastic substrate that my students have built. These you see have better IV characteristics. They actually turn off, but because they're on a flexible substrate, the maximum current tends to be even more limited by self-heating, because you can imagine the flexible substrate is not a good heat conductor. And so we're lucky that we can conduct heat to the source and the drain and to the gate, but otherwise, the current is limited by self-heating because the polyimide substrate is a very poor thermal conductor. Even so, we've reached pretty good current densities. But we're still limited by contacts, by the gate stack, and by self-heating. So you see these things, these remain problems for us in this field. Speaking of contacts, one of our contributions in the field of making better contacts with 2D materials has been to use pure gold contacts. So we've discovered about 5 years ago in 2016 that you can use pure gold contacts. It's better than using gold with titanium or chromium sticking layers. So it's very important to actually avoid the titanium or chromium sticking layer for the contact, partly because they react with either the MOS2 channel or they react with oxygen if our deposition chamber is not clean enough. And so you just end up with better contacts if you use pure gold. More recently, we've been using things also pure silver, and then some alloys with gold and indium and gold and tin very recently, but so recent that I don't have data for. But in any case, things without reactive sticking layers is very important. The other thing is to apply what's called a transfer length method very carefully. You need to include both long channel devices as well as short channel devices, because if you don't, it turns out that your extraction of contact resistance can actually be quite full of errors. And of course, to avoid transistor hysteresis when we do the electrical measurement. So we have to show both forward and backward sweeps. We need to make sure that our threshold voltage is stable and all these things. And then finally, going back to my comment about high current, if you have a study that shows low contact or claims low contact resistance, it's also important to show high current, because otherwise it's possible that there is a measurement error somewhere. So high current ultimately, I think, is what's important for applications. Okay, having said that, one way to obtain high current obviously is through better doping as well, not just through better contacts. And of course, you need doping for anything. You need doping for transistors, solar cells, and thermoelectrics, and you need both p-type doping and n-type doping. And so here's our attempts to do p-type doping of these materials. We cap them with molybdenum oxide. That's a p-type dopant for tungsten selenide here. And we've obtained some pretty good, very high current densities, actually, when we dope the material, the 2D semiconductor very highly, pretty good contact resistance as well, especially for p-type material. And then we did stable n-type doping. The reason I mentioned stable is because there are dopant methods out there which are not stable, and these are stable for months. We've tested them for months, and they were stable. And we've doped MOS2 with aluminum oxide, and that also led to aluminum oxide capping layer. I'm sorry. That led to high currents, about 700 micrograms per micron. This was actually a world record at the time. Current density, by the way, is over 100 megaamps per square centimeter, which is enormous. And the contact resistance was also pretty good as well with a highly n-doped material. The doping, of course, works. This is great. But at the end of the day, our transistors, it turns out, as I wrote here at the bottom, they are still limited by self-heating, actually, turns out, because you're pushing a lot of current through an atomically thin material that's sitting on an otherwise, thermally insulating silicon oxide. So we'll come back to that as well a little bit later, to the self-heating part, I mean. But while I'm talking about transistors, I want to highlight this 2d.stanford.edu website, where we try to benchmark things. These are data from the literature. We plot current, for example, as a function of channel length, current in these units of current density, really. And you can see that these current reports become, limited by channel length eventually, which basically means contact resistance. But you can play with the pull down menus and essentially try different kinds of way of plotting the data. And if there's some important study that, of course, is missing, which I'm sure there are some, just please let us know, and I will let the students know to update the database. To end this part, certainly we have to keep improving the mobility, contact resistance, gate oxide thickness, of course, threshold voltage. But in the end of the day, it's the current and transconductance of the transistors that matters. Okay, so I want to move on and talk about a few different examples, not necessarily electrical, but thermal, and a little bit maybe non-thermal, but maybe with a thermal flavor. And so, you can imagine if you do 3D heterogeneous integration of things into this 3D chip, the power densities become quite large. Essentially, the joke that we sometimes tell among each other is that, what we call the front end of the line is cooking the back end of the line, meaning the silicon transistors could be cooking the memory above them. Obviously, logic, like I said, could be cooking the memory. And there's a lot of interfaces in this 3D integration. And usually you have low K dielectrics. And by low K, I mean both low thermal conductivity and low electrical permittivity, which you need for high speed, components. And so, of course, we know that the current degrades when you have higher temperatures. The leakage and the reliability are also much worse when temperature goes up. In fact, they're exponential with temperature. And so the thermal properties of whatever materials go inside the 3D stack are super important. All right, so what are some of the materials that we're looking at, even aside from 2D materials? We're looking at insulators, electrical insulators that happen to be very good thermal conductors. And there's really only 3 options if you are restricted to those materials, or 3 options that I'm aware of. Maybe there's others. So here I plot thermal conductivity as a function of band gap. And of course, there's diamond, boron nitride, and aluminum nitride. And most recently, we've been focusing on aluminum nitride, although I have a new colleague at Stanford right now who's starting to grow diamond, and also another colleague that can grow boron nitride. So I think we'll be seeing more work on those 2 as well. But it's important to be able to deposit these things in temperatures and conditions that are compatible with silicon manufacturing, which is still a long ways off, especially for diamond. If you look at 2D materials, which of course are the subject of this talk, 2D materials are special because they're anisotropic, thermally anisotropic, right? So I plot here the thermal conductivity of some 2D materials in plane on the left and cross plane on the right. So you essentially see that in plane, the thermal conductivities are much, much higher than cross plane for the same material. Like let's say, graphene, graphite in plane versus cross plane by about 2 orders of magnitude or something like that. Even black phosphorus, right, is more thermally conductive in plane than cross plane. And then WSC2, you could actually make it very, very thermally insulating if you go cross plane and you stack it in certain ways. So, I mentioned earlier that our transistors are thermally limited very often. We've investigated that as well on larger transistors. It's very hard to do this on nanoscale transistors, but if you make larger transistors, you can measure this with Raman thermometry, just like a very nice talk that we saw earlier. And essentially here we measured the thermal properties of an MOS2 transistor during operation. Here we plot the temperature at every point on the IV curve for this particular transistor. And we've also simulated these things. But the bottom line, what we've learned here is that the Raman thermometry, one thing is a very useful technique, as was highlighted earlier. What I really like in this case is that you can measure not only the temperature of the MOS2 channel, but you can also measure the temperature of the silicon substrate at the same time. So it's really that temperature difference that you're most concerned about, right? The silicon substrate warms up a little bit as well, but not that much. But they get quite hot, these things, during operation, over 200 Celsius. And then what we learned from simulations is it's actually really not just the SiO2, but it's the interface between the MOS2 and the SiO2, which is a really, really big phonon bottleneck. It turns out having those van der Waals interfaces is actually bad for getting heat across, right? I guess it's not that surprising in hindsight. But when we first realized this 4 years ago, we got pretty concerned. So then, there's an expression: if life gives you lemons, you try to make lemonade. And so here's the lemonade, right? We said, well, if interfaces are so bad, what if we take a whole bunch of interfaces for 2D materials and we actually make things even worse, but on purpose, right? And so here's what we did in this case: is we essentially layered, graphene, MOS2, WSC2, a bunch of 2D materials. Deliberately, we layered them one by one, and we tried to do it very, very cleanly, so there's nothing caught between the interfaces. We were able to essentially create a very, very good phonon heat blocker because there's huge mismatch of photon density of states and these weak van der Waals bonds between layers. What I like about Raman thermometry here is that we can measure the temperature of each layer in the stack individually. So we can essentially measure the temperature difference between two 2D materials that are less than 1 nanometer apart. And those are the temperature differences that you see here, which I think is very, very cool. And ultimately, we showed that the thermal conductivity of these stacks are lower than the thermal conductivity of air, the effective thermal conductivities of the stacks. They're about 0.01 watts per meter Kelvin. So these are extremely good solid state, ultra thin solid state heat blockers. Okay, another thing that we demonstrated, which is pretty unusual, I think, is to take, layered 2D materials. In this case, this is actually just pretty thick MOS2. But then to intercalate it with lithium. So you push the lithium in, you take it out. You push the lithium in, you take it out. It sounds like a battery. We worked with battery experts to make this work. And then we measured the thermal conductivity, thermal conductance across these layers. And it turns out we are able to measure this thermal switching in real time of this MOS2 stack, right? And essentially, this is a thermal transistor because we are able to, it's kind of a 3-terminal device, if you will. You have heat flow from top to bottom, and then you have a voltage that controls the thermal conductance from top to bottom. And we modulate this by about a factor of 10x. It's not very fast, by the way. Notice the timescales are minutes. But still, to be able to modulate this, pretty fast I thought was pretty cool. We thought it was pretty cool. And we think this is good for managing thermal transients that are on these time scales. So of course, if you want to manage faster thermal transients, then you need faster switches as well, just like with regular transistors. Another example of a bit of a weird, unusual application is to take graphene and MOS2 and use them as thermal barriers. But we use them in thermal barriers in a fairly mature or almost mature phase change memory technology. Intel already sells this commercially. This is, of course, we make these devices in our lab. But phase change memory essentially needs good thermal insulation in order to be able to switch efficiently between a high resistance state and a low resistance state. So what we did is we stuck a layer of graphene or MOS2 in between the bottom electrode and the top material here, which is germanium antimony telluride, the phase change material. And we showed that putting in a graphene thermal insulation is better than the control device. And if you put MOS2 thermal insulation, it's even better. And to me, this is a little bit unusual because normally people don't think of graphene as a thermal insulator, but in the cross-plane direction it is, right? Because of the weak van der Waals bonds and the fact that phonons don't really like to travel across these 2D materials. So it is an example in a sort of nearly commercial technology, or actually commercial technology, except this was in the academic lab. The other question that we recently asked and answered, and this is a paper that these are papers that were actually just published a few months ago, and it's not strictly a 2D material, but it's kind of a cousin of a 2D material because you see the van der Waals gaps, and these are very, very thin materials. If one interface is bad, what about multiple interfaces? Of course, thermally, they're going to be much worse, it turns out, right? And so the thermal conductivity of these superlattices is quite low as a function of superlattice period here. That's the plotting. In fact, we've seen evidence of wave-like thermal transport versus particle-like thermal transport in these antimony telluride, germanium telluride superlattices. And then we took this one step further and we use it to build superlattice phase change memory. But then because we were already doing some stuff on flexible substrates, which as you know, are thermally very, very bad, we said, hey, why don't we put this on a flexible substrate? And so we did that. It turns out you can do all this directly on the flexible substrate because all of these deposition temperatures are quite low. And so here's the finished memory chip. Looks like a little potato chip because it's bendable, right? Actually, it's more bendable than a potato chip, but you get the idea. And what we found is that if you combine the superlattice that has ultra low thermal conductivity with the plastic substrate that also has very low thermal conductivity, you can get a phase change memory that actually switches with extremely low power, extremely low programming current, which is sort of a breakthrough in terms of this technology. But it's entirely done by thermal engineering, essentially, by, like I said, superlattice thermal engineering, and then even bringing in a very, very poor thermal conductor as a substrate to limit any kind of heat spreading when the device switches. So in some cases, being able to, having bad thermal conductors is actually good. Again, the spirit of making lemonade out of lemons. Okay, so I just want to summarize. I want to zoom out again, from our own work and state some of the things that I think are important in 2D materials and devices. clearly isolated improvements are not enough. I think we need to work together, academia and industry, and of course, collaborate across academia. And so very quickly, I think growth and integration below 450 Celsius is important if we want to make things compatible in the 3D silicon stack. We need good boron nitride, I think, if we want good thermal heat spreaders, for example, with 2D materials. Then we also need advances in metrology. Right now, all our 2D materials have lots of defects, and we don't have a quick way of measuring the defect densities. So metrology is super important, I think, if we want to advance this field more rapidly. And then, of course, everyone wants higher mobility. But I think having done some calculations, I think for monolayers, mobilities of about 150 are already good enough because you are able to beat silicon already at that regime, at that thickness regime at least. The contact resistance, of course, has to be lower. About 100 ohm microns is the target that we're going for. That's ohm microns because it's adjusted by the width of the transistor. And then, of course, we want stable and controllable doping. Right now, we do have stable doping, but we don't have controllable doping. And of course, these things need to be both N-type and P-type. And at the same time, we need to be very honest when we benchmark our transistors and our transconductance current and transconductance, because if we're dishonest, then we're doing ourselves a disservice, and it just becomes more difficult for industry to trust the academic results. Moore's law is not dead, I think. It's going 3D. If the economics support it, it will go 3D. Again, remember, Moore's law is as much about economics as it is about scientific progress. So of course, the economics part has to be in play. But there are massive energy efficiency benefits that are possible, I think. And of course, thermal management plays a huge role in this respect. I think for 2D materials, the most unusual and most interesting, at least applications to me, are going to be enabled by the atomic thinness and the anisotropy. And I do want to highlight that some of these 3D nanosystems actually can be built today. These are examples from the Stanford labs, carbon nanotubes, memory and sensing built on a 4-inch wafer, 100mm wafer. And this is also a 100mm wafer where my group has built some graphene analog circuits, which are done by transferring the graphene and just building on there. How can we work with industry better? Well, I think as academics, we have to get industry to buy in, but we have to keep in mind what industry is focused on. They're focused on profits and next quarter's, deliverables, right? And they're very conservative. On the other hand, as academics, we work with a few students, a few dollars or euros, and we work in labs that are held together by duct tape and chewing gum. And sometimes I feel that we also work in an academic echo chamber, where we sort of hear the same ideas bouncing back and forth, but they're not very relevant for commercialization. So that leads me to my next point, is that we really need to come up with novel, clever, and manufacturable ideas in order to really advance this field into industry. We have to be honest with our benchmarks with the incumbent technology. And we need sustained and deep funding. And I'm sure all the professors and PIs on this call agree with that. And at least in the US, I would say, I think our funding system is broken. I think there's the priorities are not set correctly. The reviews are not done correctly. I have a lot of opinions about this, but maybe that's a different talk. And it's important to talk to industry friends and not get shut out like these two cartoon characters, because that's the only way to push these things into manufacturing. Speaking of manufacturing, is this real or is this FOMO? FOMO stands for fear of missing out. I've been seeing a lot of papers recently from very serious industry players, IMEC, TSMC, and Intel, all publishing very actively in the last 18 to 24 months in 2D materials. These are prominent IEEE conferences. You see the titles all right here. In fact, right now, it feels like my group is competing with them, and we're probably soon going to be losing that competition because they have much better resources and many more people than we do, right? But it's very exciting to see this, and we'll see how the next few years, turn out. So they're clearly taking this seriously. I don't have a crystal ball for what happens next, but I'd like to end with Kromer's lemma. Herbert Kromer essentially said that applications of any sufficiently new technology will be created by that technology. So maybe this whole discussion about 2D materials for transistors is the wrong discussion, right? Because transistors may just be silicon forever, right? But maybe the unusual things that I showed you in the second part of the talk, you know, things that you cannot necessarily do with silicon, you cannot necessarily do with conventional materials. Maybe that's where the real benefit will be. I don't know. I don't have a crystal ball. I just know, for instance, that amorphous silicon, before IGZO came along, it was widely not taken seriously, but then it was, because it was used for displays and so on, as we know. So again, it's very difficult to predict the future. So I want to end right there. I want to thank a very diverse group of students and postdocs that work with me. I want to thank the sponsors, of course. I want to thank you, the audience, and the collaborators that have taught us a lot. And of course, none of this would have been possible without them. Thank you for your attention. I'm happy to take questions.
Thank you very much for this this very interesting and fascinating talk. Thank you very much. Let's have some questions. I'm sure there are many questions. Let's go for the first one. This is from Mathieu Verstraeten. Great talk. Thanks, Eric. You mentioned you want the largest possible current, but one of the advantages of TD is low voltage switching, which seems contradictory. You want control and switching, not current density, right?
Yeah, so I'm sorry, what happened to the Q&A? So, you know, when you say low voltage, how low are you thinking? Because I actually haven't seen switching in it's actually quite difficult to do switching below 1 volt, and we really need to be below 1 volt. So unless you're thinking of tunnel transistors, which are a whole different can of worms, I think it's, oh, we lost the screen sharing. Can I go back into screen sharing? I think I'll try to go back into screen sharing because I want to show something. I'll just go back to one of my transistor slides. Which one's my transistor slide? Where is it? This one, slide number 20. The short answer is I want high current at low voltage. I want high current higher than about 0.5 milliamp per micron at below 1 volt, both on the gate and the drain. That is the ultimate metric. I didn't write it down here, but that is the metric that we're going for. You can see for the drain, we're able to get at 1 volt, which is okay. We're still contact limited, but on the gate, we're switching at much more than 1 volt. And so that's why I wrote here at the bottom that the gate stack, meaning the gate dielectrics, absolutely have to be reduced in thickness, because right now our gate switching voltages are not low enough, and they must be below 1 volt. And then, yes, we will be able to get, but the metric is, just to be clear, the metric is high current at low voltage for anything that has to be low power and compete for low power applications.
Okay, let's see if there's any more questions, or maybe Mathieu wants to follow up on that question. I don't know if that's even possible.
Say it again, I'm sorry.
No, I was wondering if Mathieu wants to follow up on your answer. Yes.
Oh, I see.
I don't know if you can also see the Q&A, but now
I can. I
okay.
opened it. Yeah, okay. I did.
So he's asking, with the 2D dielectric, how low can you go?
With a 2D dielectric. Right, well, that's a very difficult question. We are using 2D dielectrics. I didn't show any of it here, but right now, well, maybe if you look in the left here, the dielectric that we're using here is just pure old aluminum oxide. And the aluminum oxide is clearly not good enough. It's not a high K enough, and it's also still kind of thick. It's kind of too physically thick, and it's not high K enough, and that's why we were not able to shut down this transistor properly in these experiments. We have looked at boron nitride as a gate insulator, but the problem with boron nitride is it has even lower dielectric constant than aluminum oxide. So boron nitride, in my opinion, is not a good choice for gate dielectrics. Maybe a single layer of boron nitride may be good just for the interface, but then you have to follow that up with a few nanometers of something like hafnium oxide or zirconium oxide, or if you're aware of it, some 2D dielectric that has a high K. And by high K, I mean, more than 15 or 20 relative K. Boron nitride, the K is similar to SiO2. And so it's just not good for low voltage switching in these transistors. Even though obviously by itself, it's a wonderful heat spreader, if you can get it. But I just think fundamentally boron nitride is the wrong dielectric material, at least for low voltage switching in transistors. It could be used as an interfacial layer, but that's would need to be followed up with a high K dielectric. Now, if you're aware of 2D dielectrics that have high K and they play well with 2D semiconductors, then I'd like to know about that, because that could be very, very important.
Okay, I think that answered his questions. Let's see if there's any more. If not, maybe I can ask your opinion on something. So it's not as much a question as more a bit of a statement also. So you're arguing that the main benefits of the 2D materials come from the regime where they're 1 layer, 2 layer, 3 layers thick, because that's where the unusual properties appear. One can also argue that another regime where interesting properties appear is when you have 2 different materials stacked on top of each other. So these interfaces, because it's not so easy to get like 3-5 MBE growth, with such a large range of different materials and get atomically clean interfaces. And I think you'll probably agree with this statement.
I agree.
Because you showed many examples of interface engineering, if you can call it
right. That. Yeah. I agree with that. Yeah, I mean, our classic example right now in my group was this thermal engineering with heterogeneous interfaces. Again, the thought here was these are very dissimilar materials that have very different phonon density of states, very different properties, but we can layer them cleanly in the glove box over reasonably large areas that we can do these measurements. And by the way, all these materials were grown by CVD. These are not exfoliated. These are grown by the students over centimeter areas. So this becomes much easier to transfer them and make the stacks. I think you're absolutely right. This heterogeneous integration, and I don't have slides here, but even Intel has done some layer transferring of germanium films over a wafer scale, which I thought was very impressive. And so, if Intel and IMEC can do it at 300 millimeter wafer scale, I think there is some promise here, I don't know what the reliability or the yield, I guess, is for such layer transfers at that scale. But I completely agree with you. I think, and again, the first application that came to mind when we started doing this was thermal, but people I know are using these kinds of heterogeneous stacks for tunnel transistors, for instance. People are using them for optoelectronic devices, right? Because you can have interlayer excitons with unusual tunable properties. I'm not an expert on those properties as much, but I see the literature work, and I talk to Tony Heinz, who's my colleague sometimes. So yeah, absolutely. I think this is much more difficult to achieve with 3D materials at this scale. And so if this can be done with clean interfaces over large areas, it could really enable some things that seem not doable with, like you said, MB growth of 3D materials. Yeah, absolutely.
Okay, let's see. I think there's another question here by an anonymous attendee. Thanks for the great talk. You mentioned a huge family of 2D materials, many thousands perhaps. It would take a long time to experimentally explore these, but could we use a computational approach to find the best of the bunch?
Yeah, I hope so. That's why I love Evan Reed. My colleague Evan Reed is the computational approach person, right? And yeah, he basically started sorting these materials not just by band gap but also by effective mass, right? And so once you start sorting things by effective mass, you can kind of get a hint of which ones may have good mobility, right? Of course, I don't think he has the scattering times for all of them. But if the scattering times could be computed, then we could even more easily figure out which ones to really zoom in on. So yeah, and the same thing could be done for thermal properties, right? So absolutely, I 100% agree that there's just no way, my 15 PhD students can study 1,000 materials in their lifetimes, right? So we need computational help to narrow it down to a few of these, which we then test experimentally to see if the predictions are correct. Yeah, we're 100% agree. And this collaboration between, of course, experiments and computation, it must continue, and it's very important. Thank you for the nice question.
I guess it gets even more complicated if you start making stacks, because then you get into, even with one interface, you have a million combinations. So
yeah, right. But first we should know the properties of the individual materials.
Right. Let's see. There's another question, I think, from Alexander Block. On the topic of heterostacks and thermal transport, even for clean interfaces, are there strategies to enhance or decrease the thermal interface conductance?
Yeah. Well, I think the if you want to decrease the thermal interface conductance, it's actually probably easier, right? Especially if you, it turns out the easiest way to do that, besides layering different materials, is to just slightly increase the gap spacing. Of course, if you increase the gap spacing a lot, then you end up with vacuum gaps, and then you're just measuring the thermal conductivity of air, probably, or vacuum anyway. But it turns out that if you rotationally misalign these materials, they don't stack exactly with the same layer spacing. So it turns out that rotational misalignment changes the layer spacing, which also changes the thermal transport. And in some cases, of course, if the rotational spacing is a little bit larger, it'll lead to lower thermal conductivity. If they're closer together, the van der Waals gaps, you have higher thermal conductivity. I don't think you can make the thermal conductivity very high like this. I could be wrong, but with a dissimilar materials, I think you can. It's always going to be worse than the bulk material. Like this is always going to be worse than like bulk, graphite or bulk MOSC2 or whatever, just because it's all different phonon properties. So I think we can make it worse. I don't know if we can make it better with a layered material like this. I don't know about in-plane. I don't know how the different materials influence their in-plane. I suspect they don't influence their in-plane thermal properties too much, because the van der Waals gaps are pretty weak, and there's not a huge in-plane kind of contribution between the layers, but we haven't measured it in this case. There's another question from David. I can just read it. With so many 3D materials available, do you think we can find new physics and functionalities? Oh yeah, absolutely. Yeah, I think so. I definitely think we can find new physics and new functionalities. I can't even predict what those might be, but like I said, my favorite example is this stack right here, but I know other people are working on tunnel transistors. I know other people are working on photonic devices. I'm sure people are working on magnetic devices as well, or I hope they are. We are not, because we're not experts in that field, but all of these I think are very interesting. And hey, if there's biological applications, I'm happy to hear as well. Also something I'm not an expert in, although we've dabbled with bioengineers a little bit, as you saw with the DNA pore work, nanopore. Yeah, I mean, I'm certainly very excited about this this heterogeneous stacking thing, especially if it can be done cleanly over large areas, because then it obviously can be done commercially.
Okay, I think it's time to wrap up this very nice NanoSeminar for today. So thanks, Eric, first of all, for getting up so early and giving this very nice presentation, answering all our questions. And thanks also for Emigdio for his talk, and all the audience for attending. I think we'll have a little private discussion with a few groups with Eric after this now, if that's okay. So again, thank you all very much for being here, and have a good day or good afternoon, good evening, until the next one.
Thank you so much.